What you are looking at is called the harmonic series. We start with 1, then add 1 by 2, 1 by 3, 1 by 4, and continue forever. The name harmonic actually comes from music and vibrating strings. When the full string vibrates, it produces a basic note called the fundamental frequency. But the string can also vibrate in smaller sections at the same time. If the string vibrates in 2 equal parts, it produces a higher note called the second harmonic. If it vibrates in 3 equal parts, we get the third harmonic, and 4 equal parts give the fourth harmonic. These vibrations naturally involve fractions like 1 by 2, 1 by 3, 1 by 4, and so on. And when mathematicians wrote down these fractions and added them together, they got the infinite sum called the harmonic series. Now here comes the real question. Does this infinite sum approach a finite number, or does it keep growing forever? At first glance, most people would feel like it should settle down on a finite number because the terms keep getting smaller and smaller. Like 1 by 100 is tiny, and 1 by 1,000 is even smaller. So intuitively it feels like eventually the additions should become so small that the total stops growing. But surprisingly, mathematicians discovered that this series actually diverges. No matter how many terms you add, the sum keeps increasing forever. And one of the most elegant proofs of this fact came from Johann Bernoulli, one of the important Swiss mathematicians from the early days of calculus. Bernoulli began with a clever assumption. Suppose the harmonic series starting from not 1, but 1 by 2 actually converges to some finite number. Let us call this value A. Now Bernoulli rewrites this same series in a slightly strange-looking way. He transforms 1 by 3 into 2 by 6, then 1 by 4 into 3 by 12, and continues the same pattern for the remaining terms. Then Bernoulli introduces another series, 1 by 2 plus 1 by 6 plus 1 by 12, and so on forever. Now, here comes the magic. Notice the denominators carefully. 2 is 1 times 2, 6 is 2 times 3, 12 is 3 times 4, and this pattern keeps continuing. You know what? 1 divided by n times n plus 1 can be rewritten as 1 by n minus 1 by n plus 1. You can verify this easily by taking a common denominator. Once we use this identity, this 1 by 2 can be rewritten as 1 minus 1 by 2. 1 by 6 becomes 1 by 2 minus 1 by 3. 1 by 12 becomes 1 by 3 minus 1 by 4, and the same thing keeps happening for every term. Suddenly, the entire series starts collapsing beautifully. When all these terms are added together, the minus 1 by 2 cancels with plus 1 by 2. The minus 1 by 3 cancels with plus 1 by 3. The minus 1 by 4 cancels with plus 1 by 4. And this cancellation continues forever. This type of series is called a telescoping series because terms collapse into each other. In the end, only the very first term survives. So Bernoulli concludes that this entire new series sums exactly to 1. Let us call this series C. Are we on the same page till now? Is everything clear? Great! Now Bernoulli performs another clever step. He subtracts the first term 1 by 2 from C. Since C equals 1, the remaining sum becomes 1 minus 1 by 2, which is 1 by 2. Let us call this sum as D. Then he subtracts the next term 1 by 6 from what remains, leaving 1 by 2 minus 1 by 6, giving 1 by 3. Let us call this sum as E. Then subtract 1 by 12, leaving 1 by 4, and call this series as F. Repeating this process again and again creates an infinite chain of smaller series whose sums become 1 by 2, 1 by 3, 1 by 4, and so on. Bernoulli then adds all these new equations together. On the right side, we get 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, and so on forever. But this is exactly the original harmonic series, and we had called this sum as a, so the right side becomes 1 plus a. Now look carefully at the left side. We get half plus 2 times 1 over 6 plus 3 times 1 over 12 and so on. Oh wow! Do you remember that this is the same as the manipulated version of the original series, which was simply a? So Bernoulli arrives at a shocking equation. A equals 1 plus a. But this is impossible for any finite number. No finite quantity can ever equal 1 more than itself. The only way such an equation can make sense is if a is not finite at all. So the assumption that the harmonic series converges must be wrong. Therefore, the harmonic series diverges and grows infinitely large. This was simply super clever. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel.